Everyone to today's Keeping Current. Sorry that I only sent out the announcement a few minutes ago. Usually I send it Tuesday evening, and I thought I had done so, but it turns out I hadn't. So people will come when they come, and we are recording the talk, so people will be able to hear it later. So we have two talks, both students of Dr. Goldsmith's, who will be speaking on aspects of social networking and COVID. It seems to me the best distancing strategy at the moment for COVID is use the network. That's what we're all doing. So this is network-based distancing, but we'll hear more details about the post-lockdown world, first from Isaac. So take it away, Isaac. You should be able to share your screen.
I will go ahead and try to share my screen. Making sure you all can see it.
Yes, that's fine. It looks good.
All right, sounds good. So yes, I am Isaac. I'm currently working with Dr. Goldsmith and Patrick Shepard, who's doing the other talk. And so I am discussing the paper Social Network-Based Distancing Strategies to Flatten the COVID-19 Curve in a Post-Lockdown World. And so the authors are listed on the screen. It was first published in Nature Human Behavior in June of this year. So this paper presents 3 strategies on how to socially distance and how best to socially distance and reduce the spread of COVID-19 in doing so. So it discusses these strategies both in network terms, such as removing edges from the network, and then in real world terms, such as stop visiting and limiting interactions in between people. And so it uses a social network to model the spread and model interactions between people. And in this network, our nodes represent individuals and people, and the edges in between them are representative of like interactions with those people. We have social distancing is currently the best way to prevent COVID, but there is a cost in that if we completely socially isolate, then there's a lot of mental health implications to that that are not great. So we want to strategically reduce our contact rather than go into complete isolation. And so we want to change the network configuration. And in doing so, we will reduce R, which is the number of people infected by each carrier of the disease. So we also talk about network distance of edges that you have to traverse in order to reach another node in the graph. So if we increase the path length, we will decrease R and decrease the spread of infection. And this is shown over in the little graphs here. So with A, there is a relatively short path length, and that gives us a much larger infection curve. Whereas with C, there's a much longer path length and a shorter, more drawn out sort of infection curve. So this paper asks if there are social distancing strategies that are easy for people to adhere to, and do these strategies actually slow the spread of COVID or of any sort of communicable disease.
Oh, were you interested in listening? Yeah.
Disease. It isn't directly discussed in the paper, is to have contact with similar people, and we will choose our contact partners based on similarity. So people who are geographically close to us or members of the same organizations, like workplaces or schools and things like that. And the purpose of this is to keep the infection localized so that we reduce the further spread. So the second strategy is to strengthen contact within communities. And so we want to keep triangles or other fours, if we follow the triangle thing. So we want to interact with people who are also interacting with another person that we're interacting with. So we want to, those who have other friends in common. And so this will also localize our infection even more so that we're spreading it even fewer places. And so we can see in the two highlighted graphs, we are reducing inter-community edges and just sort of maintaining smaller and more isolated communities. And so then the third strategy is to have repeated interaction in bubbles. And so you will decide who you want in your bubble and then reduce your contact partners rather than reduce the number of interactions with people. So everyone in the bubble will agree to only socialize within that bubble. And so some of the micro communities that the paper discusses are work units already.
You're having some network problems, it looks like.
Interacting in fairly close groups. SEIR. So susceptible Q nodes or individuals infected, and the rest of them are susceptible. So the susceptible individuals.
Isaac, let me interrupt for a sec. Your network was unreliable for a few seconds there. Could you go back to the discussion at the beginning of this slide, please?
Sure. So the model that this paper used was an SEIR model for disease spread. So each person or node will fall into one of those four categories: susceptible, exposed, infected, or recovered. And so at the beginning of the simulation, there are Q nodes or individuals infected, and the rest are susceptible. So if an individual is susceptible, then they can be exposed from an edge with an infected individual. So once you become exposed, you remain exposed for n time steps, and you cannot spread to others while you are in that exposed time. And then after those n time steps, you become infected for 4n time steps. And in the infected case, you can spread to others. And then after the 4n time steps, you become recovered and you cannot be reinfected, which now may or may not be the case with COVID, but it was sort of generally accepted when the paper was written. But so we have over here
Again, you're cutting out.
we can say this, these the yellow have exposed. Two nodes that were yellow have become red, so they were exposed and have become infected. The node that was infected has become removed, sorry, or recovered, and then the edges in between from the exposed individual, from the infected individuals have become exposed. And so in the paper, they used a probabilistic model to answer the question in the chat. It was probabilistic, so there's a certain probability at each time step that an infected individual exposes any of its contacts.
But you assume then that the graph doesn't change across time.
Yes, that is one of the assumptions. But so each node will have a certain amount of attributes that were determined beforehand before the simulation was run. So they each have a geographical location, which was determined randomly as far as I'm aware. And so they also have an age or a workplace or a school, gender, race, and other sort of fairly general attributes of regular people. So there are network ties in between close individuals and then longer random network bridges in the initial creation of the network. And so it is not a typical network creation, so it's not small world or scale free, but the closeness that they use to determine the network ties in the beginning are based on geographical location and those individual attributes. So I think the geographical location was weighted more heavily in creating those close ties. But my guess is that's something that you can change, but I'm not entirely sure about that. So they also ran a series of two sort of general simulations for comparison. So they have a null model, which has full contact on all edges, but the infection is still probabilistic. And then there was a naive reduction, which just sort of took out 50% of the edges randomly. With strategy 1, we're talking about homophily. So the sort of natural, quote unquote, instinct to interact with those that are close to us in either geographical location or in other sort of physical attributes like age, gender, ethnicity, and those sorts of things. So we only want to interact with people who are close to us. And if we do that, then it will take longer for the disease to spread to further places. So the paper gave the example of if you interact with people in a 3-block radius, it will take around 30 time steps for the disease to get 100 blocks. Whereas if you were interacting with people in a 10-block radius, it would only take about 10 to get to 100 blocks away. So we want to reduce network bridges. So these red edges that I've highlighted here are edges that are being removed in this strategy, or either removed or just not interacted on. And those I think are the same pretty much. They end up with the same end result, essentially, in this network. So. And then with strategy 2, we want to maintain triadic closures. So we will remove ties that are not embedded in triads. And we have redundant ties, which are ties that will not lead to a new infection. If we have a triad and one member is infected, it will spread along its 2 edges, and then the edge in between the other 2 members does not give a new infection. And so we say that is a redundant tie. And so the more redundant ties there are, the longer path length the graph will have. So we want to create isolated communities in the network that cannot be infected, because it does not have an infected individual in the beginning. And if they are only interacting within that triad or a smaller group without an infected individual, then there is no chance for that group to become infected in the first place. So we want to reduce network bridges even more, and then also the inter-community edges we want to remove so that there cannot be disease transfer. And then strategy 3 is very similar to the second strategy, but it is different in how to form the groups that we want to maintain. So it involves a strategic decision for interaction and requires coordinated action among all of the people that are within that small group. So it's more difficult to achieve, but it's more effective than the second strategy because you'll have smaller bubbles and more strict guidelines in interacting with others outside of the group. But it is also difficult to get people to agree to that. But so the goal of this strategy is to create isolated nodes or pairs or groups of some usually small size. So the results that the paper shared, so overall we reduce with the 3 strategies the number of infection throughout the simulation, and then we prolong the spread and lower the curve. So you can see over here in the little graph. So we delay the peak of infection and also decrease the height of that peak. And in doing so, we reduce the number of infected individuals. So all 3 of their strategies did better than both the null model and their just 50% random reduction. So I think the green one is, yes. So the green one is strategy 2, the yellow one is strategy 1, and then the red one is strategy 3. So, so strategy 3 is the best-ish of the 3 strategies. However, all 3 of them are relatively similar in their reduction of the spread. So it can be difficult or impossible to strictly use one strategy, such as with making little bubbles. You can't always only interact within those bubbles if you have, I mean, like going to the grocery store and other things like that. So the paper also discussed using multiple strategies. And so it shows the same results or very similar results using multiple strategies in the same simulation. And so we want to create small groups that are isolated from the larger community in order to reduce the spread and slow the spread of COVID. And so the paper also mentioned that their simulations were not run on large networks. So I think they used mostly 1,000 or 2,000 nodes for most of their simulations, but they postulated that it would be similar results on a larger scale of like 100,000, but they did not have the, I guess, processing power to actually run those simulations. So it may or may not work on larger groups. So as a conclusion, the social networks can model infection spread and how to reduce that spread and show how effective those strategies are in this paper are effective in slowing the spread of COVID, and they can also be compounded to increase the likelihood of compliance from individuals. So it can be difficult to get people to say, I'm only going to interact with these places on how to reduce their social impact, I guess, then it will be easier for them to comply to the strategies. And that is all that I have.
Well, I'm sure that people would like to raise some questions. I've got some of my own, so let me just begin by wondering if the authors make available their program so that other people can try it.
They do. It is, I believe, written in R. So I did not personally run it in R, but it is available, as far as I'm aware, on Nature, Human Behavior.
Good, and let me recommend that whenever people write papers, it's really nice if they provide the code so other people can verify the results and perhaps start at that point where they finished and move further. Other questions that people want to raise?
I have one. So I came in a bit late when you were talking about the topological setup that the authors took for this work, but I'm curious, you mentioned that they didn't consider large networks, but did they consider maybe other parameters with the network topology, such as average degree, density, the size of the communities within the network? Was that altered at all, or did they keep it constant for all of their experiments?
That's a good question, and I do not know. My guess is that they did alter them and then chose a certain group to run all their simulations on, but I don't know that they discussed that in the paper.
Okay, because I think that would be a cool question for this type of work moving forward.
Yeah, definitely.
I got one question too. I feel I was thinking about you like talking about the four different kind of people, susceptible and recovered and infectious, especially this three. Is that a BR? I don't think it's be quite realistic, but I feel is that be a way like people connected with infectious people to non-suspectable people and recover people and in the node between other susceptible people, so the path could be longer, and also the infectious people could also potentially enjoy the social. I mean, that would be something. I of course in the realistic we cannot even don't know who belong to the susceptible people anyway, but I'm wondering just it's like inserting nodes like between like infectious people and susceptible people, we actually insert non-susceptible people and recovered people. So make the, you know, block this kind of transaction, like transition. Does that be possible? Like something to, I don't know.
Yeah, I'm not sure. They didn't discuss anything like that in the paper. My guess is it probably would work, just given how their infection spread was modeled, but I'm not sure.
Yeah, so, yeah, just wondering. Thank you.
What surprises me is how effective the simplest method is. The simplest method was, I guess, removing randomly half of the edges.
Yeah.
Which means that if you usually would have 10 people that you would talk to or come close to, make it 5 people, and already it has an enormous effect. Well, each of us has been doing much like that. We've strongly reduced the number of people, whether it follows one strategy or another. We've all reduced. And according at least to this paper, that has already had a good effect.
Mm-hmm.
It's also striking how little advantage you get by going any deeper. That those last 3 are very similar, although they are increasingly difficult to implement. So you've got a real diminishing returns. Yeah. I did have a question about the.
I'm sorry.
Yeah, a question about the specific about the triads, the triangles, because I saw in the graphs there were cycles of 4,
Yes.
which were not being removed. But if you say that you remove any node that is not a member of a triangle, well, there were nodes that weren't. So there was, I didn't understand that.
Yeah, they also included groups of 4 in the paper. It's just a little bit weird, I guess, to talk about the parallelogram, quadrilateral. Triangle is easier to say, but yeah. So they just wanted smaller groups that were already mostly fully connected.
Other questions? Any of these modeling methods seems to me is dependent upon how accurate your model is to the real world. And my guess is that this particular way of building networks is very far from how the real world actually works. And therefore it's an interesting result, but not one that teaches us very much about what strategies we might want, because the model is so far from the real world.
One of the differences is that it doesn't distinguish between interactions. The people that you pass on the street, the people you shop in Kroger's with, and the people you live with are all the same.
It also takes no account of people who do and people who do not wear masks.
Yes.
But making realistic models is hard.
I suppose an interesting result is that if it's the case that the more fancy strategies don't work that much better, that provides no defense for racists and others who say, look, it's a smart policy to distrust immigrants, distrust Democrats, distrust all these other people. And you should divide up into tiny little tribes. Yeah, it does work, but actually just isolating in general is the thing to do.
Are there other questions or comments? Well, thank you very much, Isaac. Interesting paper and nicely presented.
Thank you.